Hello, everyone. This is Dr. Chen. We're going to start the first lecture of Principles of Physics 1. So let's start by discussing what is physics. The goal of physics is to discover the law that governs the universe, from as small as atomic and subatomic structure of matter up to what's the universe, how big is the universe, um, how universe evolved to the current state, and how many years does the universe have existed, and what's the conservation, what are the quantities that are conserved in the universe, things like that. So that's what is physics in a very brief, of course, very brief statement. And in physics, experiments are the key and the foundation of the subject. And we can say physics is an experimental science. Without experiment, physics is not existed as a science. And so what physicists does is to observe the phenomena in nature and then try to summarize everything and then come up with models, hypotheses, theories, and laws to explain what happened and then also make prediction of what's going to happen if you know the physics laws. And the theories and the laws are things that have been tested by experiment. And theories and the laws are derived and have to be consistent with the phenomena we already done. And then if you find an experiment that contradict with your theory and the law in physics, what do? We need to make improvement to the theory and the laws and trying to explain the experiment that cannot be explained by the old theory. For example, Newton's law of motion. Now it has been working very well for physicists since Newton is more than 400 years ago up to 100 years ago. For 300 years, everything works perfectly for Newton's law. And then we observe something doesn't fit Newton's law. So we need a new theory and laws, which is relativity. So in a sense, physics is also progressing and it's changing, and everything is depends on new experimental discoveries. Now, in this class, we're going to discuss kinetics, dynamics, which basically are Newton's laws. And then we discuss conservation laws, including conservation of energy, conservation of momentum, conservation of angular momentum, and the application of the laws we learned to other systems. So let's start with chapter 1. Chapter 1 is about units, trigonometry, and vector. So in this chapter, I will be focused on units and dimensions. Now, what is unit? When you're driving on the highway, your car probably tells you you are driving 50 miles per hour. But then if you have a friend in Europe, their car doesn't say miles per hour because miles is not used in Europe. Their car probably would say something about 80 kilogram per hour. And what's the difference? Why we need to learn about dimension, right? Because you need to know what is the same speed for 80 kilometer per hour in unit 50 miles per hour. So let's get started. The goal of the chapter 1 is to get to know standards and units, which is SI unit we're going to use, and be able to convert between different unit systems and to express measurements and calculate information using number of significant figures, and you need to be remind yourself trigonometry you learned. I'm sure you have learned trigonometry, otherwise you are not eligible to sign up for this class. We just need to refresh ourselves a little bit about trigonometry, and we need to learn vectors, which are probably something new for you. But don't worry, it is simple. And we can do unit algebra using its components. So as we said, let's start with unit and dimension. So we do measurement in physics for experiment. And then when you measure, for example, what's the length of a football field? What's the distance from your home to JU? And how long it takes for you to take an airplane from Jacksonville to New York? All these things are associated with a unit like 2 hours, 110 yards, something like this. So in physics, if you only give us a number, it usually doesn't contain all the information we need. You give us a number, and then you also need to give us the unit for the measurement you have. And right now, almost most of the world are using SI system. In English, it should be just the international system. Now, this is kind of a French SI. And there are 3 fundamental SI units. Because we have 3 fundamental physical quantities, 3 fundamental physics quantities, we have time, we have length, we have mass. In SI unit, the SI unit for time is second. The SI unit for length is meter. The SI unit for mass, now be careful, this time is kilogram. The SI unit for mass is kilogram. It's not gram. Just remember this. And length and time. Length is meter, time is second. Second was originally defined from the length of a day, which is 24 hours. And then most culture would cut a day into a few, like 12 or 24 equal pieces, and 1 hour to 60 minutes, 60 minutes to 60 seconds. That's how we define second in very old times. But right now, to be very accurate, we define 1 second to be this much of oscillation of the CS atom between 2 energy states. And it is extremely accurate. Now, 1 year, if you translate it into seconds, is roughly 3 times 10 to the 7 seconds. This is in scientific notation. So 1 times 10 to the 6th power is 1 million. So 1 year has roughly 30 million seconds in a year. This is how much seconds we have in a year. And then Constitution is roughly 20 years old, right? So it has 6 times 10 to the 8th power seconds. If I wonder what's the age of the universe, it has this many seconds. And we can also translate that into years. How many years are there in the age of universe? Is roughly 1.2 or 1.3 billion years. That's the age of the universe. Now this is a very, very long time, of course. Now, on the other side, the sound, the wave sound, it oscillates 1,000 times in a second. So one oscillation will take 1,000th of a second, of course. And the radio wave is oscillating 1 million times in a second. So in one oscillation only takes 10 to the negative 6 seconds. And then if you go to even smaller structure of matter, nuclear ignition, that happens in 1 to the 10 to the negative 22 second period of time. And then we move on to meter. So originally, the definition of meter is coming from the distance from the North Pole to equator. And now realize this is a bad definition because it's not 10 to the 7th meter from North Pole to equator, and it's different when you're going around the equator. The distance is different. You're going to get a different definition of a meter by connecting two different points. Now, traditionally, a few years ago, it was defined as a distance a light can travel in vacuum in 1 over about 300 milliseconds. Well, right now, the definition is tied to atomic emission. The atomic emit light, and we measure its wavelengths, and then connecting how many wavelengths equals to a matter, and it's very accurate. And the atomic clock, which measures time, is very, very, very accurate. It only loses 1 second in 30 million years, much, much accurate than the watches we have. So in terms of a length, the human size is roughly 1 meter. And if we go big, the size of the Earth, the diameter is 10 millimeters. And the distance from Earth to the Sun is roughly 10 to the 11th meter. And we can go small. Inside a human body, a cell is roughly 10 micrometer. So it's 10 to the negative 5 meter. And the radius of atom is 0.1 nanometer. And nuclear would be even smaller. So we need to familiar ourselves with this kind of notation. For example, nanometer, which means is 10 to the negative 9 meter. Micrometer is 10 to the negative 6. Millimeter 10 to the negative 3. Centimeter 10 to the negative 2. And we have kilometer, which is 1,000 meter. Yeah, so I think those are the prefix we're going to be used quite often in physics class. And then kilogram. So historically, it's just a metal, a man-made metal, and then we define it as 1 kilogram. So right now there are some progress and try to define kilogram in terms of atomic quantity as well. There's some progress, but it's too complicated for us to discuss in this class. So let's just stay with the metal inside of this picture is 1 kilogram. And we're going to discuss why different mass matters. So the mass of a human is roughly 75 kilogram, right? 70 kilogram mass of a human. So the mass of the Earth is much bigger, 6 times 10 to the 24. and then you can go small. You can find out what's the mass of a mosquito, what's the mass of a electron. Now we talk about unit and dimension. So we say we have three fundamental quantities, right? Length, time, and mass. So if we talk about length, we say we use L. See, the dimension is L, and the time dimension is T, and the mass dimension is L. So let's see what we can see with length and time. So you have a length is L, but if you have a two-dimensional area, then what's the area is, for example, if you have a rectangle, what's the area of a rectangle? You have to multiply one length to another length. So it's length times length. The area would be length squared. Similarly, if you have a cubit, you have a box, what's the volume of the box? So you need to side times side times side, length to the cube give you the volume. Then the unit, SI unit for area is meter square. Unit for volume is meter to the cube. And what's the length of the time? We can define that, okay, I cover 1 meter in 1 second. So I move 1 meter in 1 second. What's that quantity? That tells how fast I move, which in other words is speed and velocity, right? So the dimension of velocity is length over time. Its unit, SI unit is going to be meter per second. And then if I first go very slow with like I'm not moving at all, zero velocity, and then I started accelerating dash, so my velocity increase. So what's the change of velocity? You need to use change of velocity over time. And so the unit dimension of velocity is length per time, then divided by time. So you see, this is dimension of velocity, then divided by time. So it's length divided by time square, or tell you how fast your velocity change, and then we call it acceleration. So its unit is going to meter per second square. So this is unit and dimensions. So we see the dimension of velocity is length over time, and its unit should be meter per second. Three fundamental quantity: length dimension is L, length; time dimension is T; v velocity dimension is length over time; acceleration is length over time squared. Which also means if you multiply acceleration with the time, it'll give you dimension of velocity. So if you have an equation, you have to have right-hand side and left-hand side have the same dimension. So the left-hand side velocity's dimension is L over t, and the right-hand side acceleration times time. Dimension of acceleration is length over t squared, as we discussed, times time. And you can do algebra. You can just cancel a t on the numerator and the denominator, and you get L over t. So L over t equals L over t. This equation makes sense. It works. You can do the same thing. What is acceleration times t squared? Acceleration times t squared. Acceleration times t give you velocity. So acceleration times t give you v, and then you have another t, so v times t. Now dimension of v is L over t times t will just give you L. So you can have length equals acceleration times t squared, and it means that the dimension works. And we're going to explain what this coefficient means. At least if you have an equation, you see the dimension of left-hand side and the right-hand side has to equal. So You can do algebra with unit and dimensions. They're just something we need to be careful with. If you want to add or subtract two quantities, they have to have the same dimension and best have the same unit, so you can directly add the number together. You can only equal two quantities that have the same dimension. And arguments inside the trig function are dimensionless. And the logarithm and exponential function, their arguments are dimensionless. Now let's move on to uncertainty and a significant figure. Start from a simple case. What is significant figure? You probably have learned. So you look at the number. You start from the number on the very left and count how many number you have. For example, this one you only have one digit, so it's one significant figure. And this one, those 2 zeros doesn't really matter for significant figure. We start for 7, 1, 2. So this 0.0075 has two significant figures. What is this one? 1,500 grams, 1500. This one actually has four significant figures. And in scientific notation, if you write it as 1.500, it tells you you are pretty sure, you are very confident that at this place, at the 1 gram place, is 0. So this measurement gives us four significant figures. Now if you write it as 1.50, 10 to the power of 3 gram, so which means you are pretty sure about the 10 gram place is 0, and you don't know, you actually in the 1 gram digit, you are not quite sure what the number is. And so for this one, you only have 1, 2, 3. So this number is much more precise than this number. And you can do the same. This one only have two significant figures. So this one tells you I only know those two numbers is very precise, and it could be 1 or 2 or 3 at this place, which I don't know. And this one tells you 1.500 tells you here is exactly 0. And the 1.5 10 to the 2 tells you I don't know what's there. There is 1.5 has two significant figures. So that's what significant figures means. So I cross this, which means I do not necessarily agree with this one. I think this one should have three significant figures as well. Okay, how to add two figures together? For example, you have one measurement that gives you 123. You have another measurement which is very accurate, 5.35. Add them together. Mathematically, you're going to add 128.35. But since I don't know what's this, I don't know what is after. I don't know what is after this 3, 123 point. So you add 3 to something you don't know, it doesn't really make sense for you to keep those two, because this 35 is added up to something you are not sure of. It could be 1, it could be 2. So the best thing we do, we only keep it as accurate as this number, the least precise number 123, and the sum would be simply write as 128 rather than 128.35, because you really don't know for this measurement what is in the decimal points. And similarly, now your first number equal up to this, your second number equal up to this, so you can keep it up to 1,000th of 1. So you can keep this 4. So the answer is 0.004. Now how about multiplication? So if a rectangle, you want to measure, you have to calculate what's the area. Now the unit of area is centimeter, right? So you just multiply them together. Mathematically, you punch that into calculator, you get 33.35. But I only know this side by two significant figures, 4.5. Now this side, three significant figures, 16.3. Now in multiplication, you can only keep your answer, the significant figure of your answer, equal to the same significant figure of the least input, which in this case is 4.5, right? 4.5 has two significant figures. So you can only keep two significant figures for this calculation. So you should write your answer as 73 centimeter squared. Unit conversion. Now, this we need to know 1 mile is 1,609 meter. You can also write it as 1.609 kilometer. 1 kilometer would give you 1 kilometer give you 1,000 meters. And 1 feet is 0.304 meter, which in terms of centimeter is 30.48 centimeter. If you convert it to inches, 1 meter is 39.37 inch. 1 inch is 2.54 centimeter. So for one example, let's convert 15 inch to centimeter. 1 inch is 2.54 centimeter. And we should say 2.54 centimeter over 1 inch give you 1. And well, we need this one to be to this kind of conversion to the unit conversion. So let's see. I want to convert 15 inch to centimeter. So I want to get rid of inch. I want to keep centimeter. So I multiply 15 inch by a 1. You can see this one is nothing but just 1. You multiply any number by 1, it will give you back to the same number. So whatever I have here still gives me 15 inch, right? But the good news, I have an inch in the denominator, I have an inch in the numerator, so they can cancel each other. So what's left is 15 times 2.54 centimeter. You just do your calculation. What is 15 times 2.54? Give you 38.1. You keep the centimeter. This is how many centimeters do you have in 15 inches. Now let's do one more example, which is a question we have at the beginning. Convert miles per hour to meter per second. I have miles per hour. I want to get rid of miles an hour. I wanted to keep meter in the numerator and second in the denominator. So I need to know how many meters do you have in 1 mile. I multiply a 1. With, so 1,609 meter divided by 1 mile. So 1 mile equals 1,609 meters. So 1,609 meter divided by 1 mile give me 1. 1 hour has 60 minutes. 1 minute has 60 seconds. 60 times 60 give you 3,600 seconds. So 3,600 seconds equals 1 hour. So 1 hour divided by 3,600 seconds give you 1. I'm multiplying a velocity by 1. This is a 1. This is also a 1. You multiply anything by 1 and give back to yourself. Alright? Okay. So now I do the cancellation. I cancel hour and hour. I cancel mile and mile. So I leave with a bunch of numbers. 65 times 1 times 1,609 divided by 3,600 divided by 1. I only left the unit is meter in the denominator, second in the numerator. Oh, sorry, meter in the numerator and the second in the denominator. And after you do the calculation, this number gives you 29. So now I'm comfortable to say 65 miles per hour equals 29 meters per second. So this is how fast you are driving on highway, roughly 30 meters per second. In 1 second, you moved 30 meters. And in physics, sometimes it's also useful. We just estimate it up to what's the power of 10. For example, the mass of a human, 75 kilogram. If you round it up, the closest you can get is 100. You round it up to a closed 10 power of 10th is 100 kilogram. This is order of magnitude calculation. It's not very accurate, but a lot of the time it's just do the job.